welcome guys. Yeah, so hope you guys subscribe to my channel. So today we keep talking about a new topic. Yeah, so so let's talk about subsequence. So today we talk about subsequence and sequence. So let me just quickly say what's subsequence. Yeah, so subsequence is a easy idea, right? So suppose you have Xn from 1 to infinity, right? And then you can pick up like n1 less than n2 less than n3, keep going, and create another sequence. Basically, is Snk, right? So k from 1 to infinity. So basically, you pick up whatever you pick, whether you cannot change the order. You cannot change the order of the sequence, and this is called the subsequence. Okay. Okay, so the theorem, which is astonishing, is that right. So if you have Xn, which is a sequence in a compact metric space X, then there exists a subsequence k from 1 to infinity converge in X. Okay, so yeah, so basically this is like the Weierstrass or the Weierstrass theorem, also called Weierstrass theorem. Okay, so B is that the bounded sequence. So bounded sequence. So basically your sequence cannot go to infinity. Bounded sequence in Rn has converge subsequence. Okay, so this is the usually the people like to talk about this theorem, just pronounce whether A or B. Okay. Yeah, so proof. Yeah, so since we have the idea of compact, and we already talked about compact implies closing bound, right? Yeah, so let's see how to prove E, right? So this is what we already proved a theorem. Let's see, right? So we already to prove a theorem about compact. Okay, so let me just right. So basically we have proved. Okay, so remember about the compact, then we have the following. So we have the following that if E is compact, then you can show that if every infinite subset, every infinite infinite subset of E has a limit point in E. A limit point in E. Okay, so yeah, right. So we have this. Okay, so we can use this theorem, right? So that's that E to be the image. So E as a set of just take all the P1, all the X1, X2, X up to infinity, right? So we take this as a set. Okay, so there are two cases, right? The first case, so E is a compact set, right? Because I mean, okay, so I should not say it's a compact set. I should say the yeah, so I should say the E is a compact E is a subset of X, right? So subset of X. Okay, and I can consider its closure, right? So I can consider its closure. So closure is also in X because X is compact, right? So X is compact, so you take closure, it becomes this, right? So the closure is still in X, right? So E closure is compact. E closure is compact. Okay, so there are two cases. The first case is that E is finite. E bar is finite, right? If E bar is finite, it means that you have a point, you have a series, you have a subsequence which happens infinite times, right? So you just take that one. So for example, let's say xi equals to 5 happen infinite times, then you just pick 5, and it becomes a converged subsequence. Okay, otherwise otherwise E must be infinite, right? So by this theorem, you can take you can find the limit point, right? So for epsilon greater than 0, there's a point in the set E bar such that the dp with that limit point, right? So limit point X, maybe equal to X0 is less than epsilon, right? So you can pick epsilon be 1 over n, and then pick up this p to be that, call it xn, right? So you can always find such p. Obviously, that xn converge x to s zeros. Okay, so we'll prove this theorem. Just a reminder. Let's see. Yeah. Also, that point is in x, right? That point in x. The reason is that x is compact. Okay, so basically we prove A. Okay, we prove A. Okay, so B is also B is almost trivial, right? Because we already proved A. So we know that every bounded subset. So every bounded subset in RK. So let me just write down every bounded subset in RK is containing some compact sets in RK. Then by A. We prove it. Okay. Okay. So another theorem is that right. So given any sequence that's called Pn, right? You can take all the converged subsequence. Okay. So you can take all the converged subsequence. So let me write down a set S. This is which x is a converge. Basically, x is a point converge from taking the subsequence of Pn. Okay, so you can pick out different subsequence and collect all of it and call it S. Okay, S is a converge point from taking all the subsequence of Pn. And the theorem is that what? The theorem is S is closed in X. Right. So remember that all the sequence are in X. Then, so this is our results. Okay. See the proof. Okay, so proof. Yeah, I think. Let me see how to prove. Okay, so in order to prove S is closed, right? We are trying to prove what? We are trying to prove the limit point of S. So the limit point of S. I find it out, right? Maybe write this sentence many times. A limit point of S in S. Okay, so let's take this. Let's call it the limit point of S is called Q. Okay, so let's call Q. Okay, so let's choose. Let me choose N1, such that Pn1 not the same as Q. Okay, so why this is it? Why this N1 is this, right? If N1 is not this, means that every Pn is just Q, right? So by definition, Pn belongs to S. Okay, so there must be this such N1. And I let delta to be the distance between this Pn1 and Q. Okay. And right, that's Q, right? Okay, and let me just keep going so I can choose N2. Let's just N1, N2, and choose maybe up to Ni minus 1. Okay, so I just pick a lot of subsequence such that it's not the same as Q, right? So by definition, Q is a limit point of S, right? So there exists X belongs to this S such that it's arbitrarily close to Q, right? So your dx Q can be arbitrarily small, So let's choose it to be delta divided by 2 to I. Okay. So X belongs to S, right? S belongs to S. So X is a converged subsequence, right? So you can find another one, one called Ni such as Ni minus 1, right? Because X belongs to the converged subsequence. So you can take that represent the subsequence and then pick out Ni larger than Ni minus 1, such that your dq Pni is less than, let's say, right? So now less than arbitrary, right? So let's take delta to be 2, also the same as delta divided by 2i. Okay. Okay, so what we already show is what? What we already show is that from these two you can get a dq Pni, right? Because you can Oh, sorry, this is x. I'm stupid, right? This is x. So the x p n I is this, and the dx cube, right? So from these two, you can get your d or q p n I less than the sum of it. So 2x plus x p n I, right? So which is a delta to I minus 1. Right. So what this means? What this means that P and I, right, is amazing converge to Q, right? Because I can take I to infinity. Right. So we prove that the Q come from some subsequence of P, which proves that Q belongs to S, which means that S is closed. Okay, so this is subsequence. Yeah, and to start from here, let's talk about another topic called Cauchy sequence. Yeah, probably this is also the most important idea in the analysis. Cauchy sequence. Okay, so Pn is a code in X, right? It's a Cauchy sequence. It's Cauchy. Means that for epsilon greater than 0, and you can find let's say some integer n such that when maybe I use larger n, such that when m n larger than n, you will have a dpn dpm less than epsilon. So basically, it's a little bit different from converge. Right? Converge means that you can find some point p such that the dp and dp less than epsilon. But now I'm saying that up to n, up to some n, every point from the left, every 2 points is restricted to less than epsilon. So it seems from you that maybe Cauchy is better than, is stronger than the usual convergence. But actually what? Actually means actually is that if Pn converge, then the Pn is Cauchy. Okay, so this is the theorem that I'm gonna to prove. Okay. Theorem. So basically Pn converge means that the Pn is Cauchy. Okay, so so let me just write down the words, right? So converge means that for epsilon, right, you can find n, let's say n, right, such that when n greater than n, your dpn you converge to some p, right, less than epsilon, right? And but the Cauchy means that from n, your any 2 points constraint, right? So this is trivial, right? You just take this to be epsilon divided by 2. That means for any m, another m greater than n, your dpn is less than epsilon divided by 2, right? So you can easily prove that your dpm that's equal to dpnp plus dpmp, right? Triangular inequality. So this is epsilon. So which you prove that you just pick a such n, such then for every mn greater than this larger n, your dp and pm is less than epsilon, right? So this proves that pn is Cauchy. Okay. Okay, so from now on, that's another idea is called diameter. Okay, so take the non-empty subset in X. Maybe this is not good notation. I should write as this. Right, so take any non-empty subset X, you can define a diameter E. So by diameter is like this, right? So your belief is that it should be larger. So you somehow try to pick up the PQ, right? So such that the PQ belongs to E. So it should be PQ both belongs to E, right? And then you want to take the minimum, maximum, right? But there's no maximum there's no maximum idea in the usual. Maybe there you cannot get a maximum, right? Because if there's no, if this boundary do not include in this set, so real analysis ideas that take the so-called soup. So suprema, okay. It's called diameter of E. Okay, so there's another definition. So another definition. So I will not prove for you, but you can check. So another definition for a Cauchy, Cauchy. Cauchy is that let's say you just let En, right? So your En to be your P1, P2. So you take it as a set, right? As a set. Sorry, as a Pn plus 1, Pn plus 2, right? You just for each n, right? You take this Pn. as a set, right? So for each larger n, there's a set larger En. Then Pn is Cauchy. By definition, right? If diameter of En goes to 0, as larger n goes to infinity. Okay, and so you should check that this definition the same as the previous definition. Exercise, not difficult. Okay. Okay. Okay, so and we proved that. So let me just write down. We proved that every converge is Cauchy. Okay, so B is so this is what we already proved. Okay. Yeah, so let's prove another one is that if X is a compact and Pn is Cauchy. So somehow like you need to add some condition like compact, right? So that's why compact is so important. Okay, so then the Pn converge in X. So basically the converge point P will in X. So somehow compact plus Cauchy give you converge. Okay. So yeah, so we need to prove this. Okay, C in RK in a Euclidean space, every Cauchy converge. Okay. Okay, so let's prove. This is the most important part. Okay, so let me just quickly prove. We already proved A, right? So let's quickly prove B implies C. I think it's trivial, right? Because if you have a Cauchy sequence and I mean from B, right? You know, yeah. So let's see. So you might believe, you might not believe that you might not you may not say that, oh, but the RK is not compact. Yeah, I mean by definition this is true, right? But you can take the diameter, right? So you take some diameter. Let's say for some n, you take some diameter En, right? And by definition, this diameter will shrink to 0, right? So you can make it less than 1. Okay, so this will make it. This will make it what? This will make the Pn plus 1 up to infinity. This guy is bounded. And we proved that every bounded subset in RK can be covered by some compact set. So basically, you can pick a large cube to cover it. Then you by your second theorem, right? So now you can use X as a large cube, and the Pn is Cauchy, so Pn converge in this. Okay, so B implies C is trivial. Okay, once you notice that every bounded subset can be covered by some compact set in the RK. Okay, so let's prove B. So probably B is the important part. Okay, so let me use the diameter definition so you make it easier. So Pn is a compact. Let's say Pn is a Cauchy sequence in compact space, and right. So we have this. So we can define this as En, right? So I should say right as set. So En goes to 0 as n goes to infinity, right? Diameter. Right. So right. Okay. Yeah. So one thing I want to say that if diameter goes 0, you can check it. It's the closure is also 0. Okay. Right. So and the things that you can since this En goes to 0, right? So when n large enough, this En will become what? Will become compact. This En will let's say will close. Sorry, will En will. I'm stupid, right? So now we are working in a general matrix space, right? So I cannot use the closed and bound implied compact, right? But I mean I can still say that En bar is closed, right? Because this is closure, and the X is compact. And then there is a theorem that we already proved is the closed subset of compact set is compact. Okay, so we can say that En bar is compact. Okay, so right, so En bar is compact, and by definition, right, by definition, we get what? We get the En plus 1 bar is less than is contain En, right? Okay, definition, right? So we can use the Cantor intersection theorem. Okay, we can use a so-called Cantor intersection theorem. Says that you can just prove this, right? You just use, right? And the Cantor intersection theorem that says that there now every compact set finally there will exist at least one point, right? It's non-empty. Okay. But you know the diameter of En bar is 0, right? As n goes to infinity. So which means that finally you cannot contain 2 points, right? Otherwise, if you contain only 2 points, then diameter will be non-zero. Right? So the only case is that finally their intersection only contains 1 point. Okay, so there's a final point Q, right, inside this all intersection. Okay, so there's a cube, right? So inside every intersection, only one point cube. Okay, so remember that the diameter is a definition of soup, right? So that means for epsilon 0 greater than 0, right, you can find the integer and 0 such that the diameter En bar less than epsilon. Okay. Also, this is by converge to 0, right? For n greater than n bar, right? So when n greater than n bar, n0 bar, sorry, n0, okay. And right, so let's take this. So by definition, right, Q belongs to this En bar. Right, Q belongs to En bar, and the diameter of En bar is 0. So every point P in En bar satisfy what? Satisfy dpq, right? Less than epsilon, right? Because this is a diameter, right? So we have this. So every point in P in En bar satisfy this. So remember that what we need to prove is it converge, right? So we hope to prove that it converge to Q, right? So from now on, you see the trick, you see the answer, right? Because for any epsilon, you can find this. So let me just read it. For any epsilon, you can find n0 such that when n greater or equal to n0, then it is the point in En bar such a deep. I mean, this is the every point, right? I can weakly see statements that there exists a P in En bar such a dpq that's epsilon. Okay, so right, so which tell you that what, which is a P. So I can pick up epsilon to be 1 over n, right? And I can find such Pn. So the old trick, so Pn converge to Q. Okay. Yeah, so this is the statement. Okay. Also notice that yeah, okay. Okay, yeah. So the proof. Okay, so let's give another definition, which is also important one. So the X metric space is called complete. So remember that we didn't prove, we only show that so we prove two, right? Converge implies Cauchy, and also in compact space, right? In compact space, Cauchy implies converge. So we can result say that X is called complete space, complete metric space, if every Cauchy implies converge. Or I should say every Cauchy sequence converge in X. Okay. Converge in X means that the final converge point in X. So example is that the usual RK, right? So the Euclidean K dimension, the Euclidean space is not compact, right? But in his case, Cauchy still implies converge. Okay, and the reason is that in our Euclidean space, right? If you have Cauchy, that you can still find Q, which is a compact, and the cover that Cauchy, right? So in an RK, even though you don't have compact, then you can still cover it by compact. Right, so somehow Cauchy sequence cannot blows up, right? Because its diameter is fixed. Its diameter will shrink up to some point, right? So yeah, and yeah. So next time we talk about the monotone converged theory. Okay, see you guys next video.